On this first one that we're going to talk about, this is some probability stuff. I want you to imagine that in 10 years you go to a class reunion, and no, let's make it 5 years. We'll make things entertaining. So in 5 years you walk into your class reunion and there's somebody, we won't name any names, and they have two children, okay? And you ask them a question. You say, oh, you have two children? Is the oldest a boy? And person says yes. And then she gets distracted and you're going to ask, is this other one a boy? So what's the probability that both of them are boys? Okay. Or now let's imagine that you ask this question instead. So you walk up to this person and you say, is at least one of them a boy? And again, what's the probability? She gets distracted and doesn't have a chance to tell you. Well, she says yes, one of them is at least a boy, but she doesn't say that they're both boys or there's a girl. So what's the probability that both are boys? So again, on both of them, we have the same question. What's the probability that both are boys? So you're thinking, well, it's 50-50 chance, right? Well, that's not the case, and let's explain why. So if the oldest is a boy, then the second child is either a boy or a girl. So there's only two possibilities. They're both boys or both girls. So this one is a 50% chance, okay? But on this one, all that we know is that at least one of them is a boy, okay? So that means that the first child could have been a girl or the first child could have been a boy, right? So at least one of them is a boy. So we could have a girl boy, right? We don't know. It could be a boy girl, or it could be a boy boy. We don't know which of these. But notice out of these, there's only 1 in 3 possibilities that it's boy boy, knowing that at least one of them is a boy. Okay. Now, to give a better understanding, if there's two children, what is our sample space? CHILD. You could have a boy and a boy and a girl, or you could have had a girl first and then a boy, or two girls. So these are all the possibilities of two children. It has to be one of these four. Okay, it has to be both boys, both girls, a boy and a girl, or a girl and a boy. There's not anything else that it could be. So when we know at least one of them is a boy, we are looking at these three. Okay, and then both of them being boys, there's only one out of these three that are both boys. So anyways, kind of some interesting probability with that. But this is kind of an introduction. So all the possibilities is called the sample space. Okay, so when we see all the possibilities, that's called our sample space. Then you have to read the question carefully, knowing that the oldest is a boy. The boy came first. Now we're only looking at 2 of our 4, and both of those being boys, there's 1 out of 2 of those. So depending on how the question's worded, changes the probability of what we're looking at. So here's our next question. Suppose you have 3 doors. I don't know if you've ever seen Let's Make a Deal, and you guess one of these doors. You can see the prizes up on top, but for this, pretend right now you don't know what the prizes are. So you have 3 doors you can choose from. You have door number 1, door number 2, or door number 3. Okay, so what happens in this Let's Make a Deal is you choose a door. So let's just suppose you choose door number 1. If you choose door number 1, that's supposed to be a glass of water. Anyways, I don't know if that's really looks like a glass of water, but use your imagination. That's why we have artists in the world, is they can make it look like a glass of water. But if you choose door number 1, now what's going to happen is the game show host is going to be like, all right, you chose door number 1. You don't know what's here, but I am going to show you what is behind door number 3. So door number 3 gets opened. So door number 3 gets opened up. Okay. And you look behind door number 3 and there's a flower. So you know that door number 3 is not correct. Now, when you first started, the chance that you chose the $1,000 out of these 3 doors was 1 out of 3, right? Because you have 3 doors, you just randomly pick one. The chance that you get it right is 1 out of 3. But now you know that this door is incorrect. Okay? So you chose door number 1, and they did not open that door. They never opened the door that you chose. And so they're going to say, do you want to switch or do you want to keep your door number 1? Now, obviously, you can see that this is where you want to be, but you want to switch, okay? And you switch and you choose door number 2, you win, okay? So you chose door number 1, you switched, you win, okay? Now, let's start this over again, okay? So you chose door number 1, you switched, and you win. Let's say you choose door number 3 first this time. Well, you know that they're not going to show you door number 2, because they're not going to be like, okay, here is the cash, because then, of course, you would switch. So they're not going to say, well, why don't you open door 2 and see the $1,000? Do you want to switch now? You're going to be like, oh, yeah, I want to switch. But they don't do that. So instead, since you chose door number 3, they're going to open door number 1, and they're going to say, there's a glass of water behind door number 1. Do you want to switch, or do you want to keep your door number 3? Okay, so let's say you switch. You win. Yeehaw. Okay, now the only other option that you could start with now is, let's say you choose door number 2 first. So you choose door number 2 first. They show you door number 1 and you're like, yeah, that didn't work. So you switch. You lose. Okay, now let's go back through these and see what would have happened if you wouldn't have switched. So you choose door number 1, they show you door number 3, so you cross it off. You don't switch. You stay with door number 1, you lose. Okay, you choose door number 3 first, they open door number 1. You don't switch. You stay with door number 3. You lose. Okay, you choose door number 2. You don't switch. You win. So by not switching, you win 1 out of 3 times. But by switching, you win 2 out of 3 times. Okay, so it's kind of a weird thought, but by switching, you win more than you lose. Okay, the reason being is, if you, with 3 doors, if you choose one door and it's wrong, then they're going to show you another door that's wrong. Okay, kind of like what we have here. You chose door number 1, it's wrong. They open door number 3, and it's wrong. But when you switch, you win. And the same thing for door number 3. They're showing you door number 1, you switch, you win. So the only where you lose when you switch was if you had somehow chosen the door right the first guess. But your chance of guessing the door on the first try is 1 out of 3. Okay? So there's 1 out of 3 chance that you chose the correct door. But when they show you a door is wrong, you now have a 50-50 chance, okay, of getting that right. But this is the weird thought. Here's the weird thought. You had a 1 out of 3 chance in getting yours right. Okay, that left another 2/3. But they automatically show you one of the other doors, and that crosses it off. So you had 2 doors that you didn't choose, but one of them's wrong. So this one has better odds of having the right one in it. So the 2 out of 3. So you're better off to switch to this one because they canceled one of them off. So 1 out of these 2 was the winner. So the 2/3 gives you a better chance at it. That part's kind of confusing. I probably didn't explain it the best. But that's the idea with Let's Make a Deal. So as you can see down here with the example, that happens every time. And so if I were to give you 4 doors, okay, so if you get 4 doors to choose from, door 1, door 2, door 3, and door 4. If you walk up to any door right at the beginning and choose one, the chance of you getting it right is 1 out of 4. Okay, so let's say this one has the dollars, $1,000. This one has 1 cent. This one has a nickel, and this one has a dime. Okay, so if you choose door number 1, the chance of you getting it right, choose door 1, the chance of you getting it right is 1 out of 4. Okay, there's only 1 door out of these 4 that is correct. So you choose door number 1. They show you door number 2. And it's wrong. So now you can say, well, do I want to keep this or do I want to switch to one of these? Okay, so let's just suppose you switch. So you switch on the first one, you lose. Okay. Now let's say you go to door number 2. So you open you chose door number 2. Oh, so when you switch, the probability of getting it right is 1 out of 3, right? So anyways, you choose door 2. They show you door number 3. Okay? So door number 3 doesn't work. So now you have, if you switch, one of these could be the right answer. So you have a 1 out of 3 chance. If you choose door number 1, you win. If you choose door number 4, you lose. Okay? So choose 1, you win. Choose 4, you lose. But your chances of winning by switching right here is 1/2. That one's, hold on, that's not right. All right, so let's go to door number 3. You choose door number 3. They show you door number 2 again, it's wrong. So if you switch, you switch. If you choose 1, you win. If you choose 4, you lose. Okay? because they opened door number 1. So now you're on, or door number 2. Now you're to door number 4. So you choose door number 4 first of all. They show you door 2. If you switch, you could either choose door 3 or choose door 1. Okay? So what I'm trying to say is when you chose the door right at the beginning, there was 1 out of 4 chance that you got it right by just randomly guessing. Okay? This one, if you choose door 1 first, there's 3 options for them to show you of incorrect doors if you chose the first one right. But if you choose a wrong door, such as these ones, then they're going to open another wrong door. And so by switching, you have a much better chance of winning than staying. Okay? And if you stay on each of these, you lose. So if you stay on each of these, you lose. Okay? But by switching, you have a 50% chance of winning on these 3. So even if you were but if you stay on these 3, you lose. Okay? The only one that you win on if you stay is this one, which is your 1 out of 4 chance. Whereas these ones, if you choose to switch, okay, you have a much better chance because there's only 2 doors that you're going out of versus 4. So your chance of winning on these is 1/2, 1/2, and 1/2. Okay? So anyways, the main idea of this is your probability goes up a whole bunch when you choose to switch of choosing the right door. Because the only way that it goes against you is if somehow you're very lucky and on that first door you chose the right one to begin with. Okay? So much like this problem here, the ways to win by just random luck guessing out of the first way is 1 out of 3. But if you switch, it's 2 out of 3. Okay, this way, there's 1 out of 4 ways of guessing. If you switch, you get 1/2 will win and 1/4 of them will lose. Okay? So, anyways, that's the random Monty. They call it the Monty Hall show because that's the name of the host with Let's Make a Deal. Just a quick thought. Maybe this will help make this a little bit more clear. Let's suppose that you chose door number 1, and I decide to show you 2 doors. So this door and this door are both incorrect. Should you switch or should you stay? So, out of the 4 doors, you had a 1 in 4 chance of getting it right. I just showed you that 2 of them are wrong. So should you switch or should you stay? If you switch in this case, you lose. If you stay, you win. Okay? So now let's suppose you chose door number 2. So you choose door number 2. I show you 2 wrong doors. Should you switch or should you not switch? If you switch, you win. If you stay, you lose. Okay, so let's now change to another door. Let's say you go to door number 3. You choose door number 3. I tell you that door 2 and door 4 are wrong. If you switch, you win. If you stay, you lose. So now we go to the 5th door. Or the 4th door, you choose door 4. I show you that these 2 are wrong. If you switch, you win. If you stay, you lose. Okay? So if I take away 2 doors and you stay with the one that you originally chose, there are 3 ways that you'd. So if you stay with the door that you originally chose, you lose 3 out of the 4 times. If you switch, you win 3 out of the 4 times. Okay? So as you can see by this, much better odds of switching than staying with the one that you had at the beginning. So the odds of you getting it right the first guess is only 1 out of 4. But if I take away 2 of the doors, okay, because I'm showing you 2 wrong doors, well, the chance that you guessed it right the first time is 1 out of 4. So that means, boy, this one's probably got a 3 out of 4 chance that it's right if the other 2 have been taken away. Okay, so this has a much better chance of being right, knowing that those 2 are wrong. Okay, so again, you'd have to know that these are wrong, but there's so much better chance. It's kind of like if I had 10 doors. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. If I had 10 doors and there's only 1 right, so this one has the $10,000 in it this time because there's more doors. Well, if you choose door number 1, and I show you 8 of them that are wrong. Okay, so I'm going to show you 8 of them that are wrong. So I'm going to show you this one's wrong, 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 and this one's wrong. Are you going to stay with the one you chose originally, or are you going to choose the one that I didn't show you? Okay, the chance that the door you chose right off is right is 1 out of 10. But now since I know all of these are wrong, this one has a 9 out of 10 chance of being right. Okay, because I know these 8 are not correct, so the chance of this one being right is 9 out of 10. So you'd have much better chance of switching knowing that these 8 are wrong. Okay, so it's not just 50-50%, it's not 50-50 chance. No, it's a 9 out of 10 chance that this one is right. Okay, so originally you only had a 1 out of 10 chance to get this one right, but now the other one that's right is within these 9, correct? So I have 9 more boxes. One of them has a chance of being right, correct? Being correct. So this has a 1 in 10 chance of being right. The other 9, there's one of these could also be correct. So there's 9 boxes that could be correct. But once I know that 8 of them aren't, boy, that really makes my odds. So 1 out of 10 that it could be right here, or 9 out of 10 chance that it could be here. So that's, anyways, another way to look at it. Okay, I want you to imagine you're playing a game that involves 2 dice. Okay, we're going to create the sample space for these 2 dice. So the first dice you roll is red. So it's going to be a 1, a 2, a 3, a 4, a 5, or a 6. Okay, but now I'm going to roll a black dice next to it. Well, this black dice could be anything from 1, 2, 3, 4, 5, 6, right? And if I had a 2 on my first dice, the black dice could still be a 1, 2, 3, 4, 5, 6. 6, 5. I guess it covers all the numbers. 1, 2, 3, 4, 5, 6, and so forth. Okay. So the red dice, whoops. So the red dice could be like this. And so forth. And then we get the black dice that could be all of these choices. So this is our black dice. Now what's interesting on this is if we add these pairs together, so 1 plus 1 makes 2, 2 plus 1 makes 3, 3 plus 1 makes 4, 4 plus 1 makes 5, 5 plus 1 is 6, 6 plus 1 is 7. That makes 3, 4, 5, 6, 7, 8. That makes 4, 5, 6, 7, 8, 9. That makes 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. So that's if we add them together. So if I ask you, what's the probability that you roll 2 dice and you get a sum of 8? Well, these are the ones that have 8. So there are 1, 2, 3, 4, 5 ways to get a sum of 8 out of. There's 6 this way and 6 this way. So there's 36 total because that's like the area. You know, if we have a 6 by 6, the area is 36. So there's 5 ways out of 36 to get 8. How many ways are there to get a 7? 1, 2, 3, 4, 5, 6. 6 out of 36, which is 1/6. Okay. So how many ways are there to not get a 7? Well, if there's 1 out of every 6 ways is a 7, 5 out of 6 ways is not a 7. Because remember, these two have to add up to be one whole. So it either is a 7 or it's not a 7. And together those add up to be 1. So probability always has to add up to be 1 if you do an event and its complement is what that's called. So the event of it not happening. So what's the probability of getting a 5 or less? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 ways of getting a 5 or less, which means there are 26 ways of getting more than 5. Okay, so you should reduce these. You know, that should be 13 over 18, and this should be 5 over 18. But see how those combined make a whole 36 out of 36 or 18 out of 18? So that always works. So here's another question for you. Let's suppose you have a room full of people. What's the probability that 2 of them have the same birth dates? Okay, so what's the probability that 2 people in a room have the same birthday? So that's kind of a hard problem, but what we're going to do is we're going to say, what's the probability that they do not have the same birthday? Okay, so now think about it. Have the same birthday? Is 1 minus the probability they don't have same birthday, right? Because remember, those have to add up to be 1. So if I know that they don't have the same birthday, I can say 1 minus that, is the probability they do have the same birthday. So they don't have the same birthday. Well, how many ways are there for let's say we have two people. How many ways are there for the first person to have a birthday? Well, 365 days out of 365, right? Now, if the second one does not have the same birthday, how many choices does he have to be born or she have to be born that they don't have the same date? Well, she could choose 364 because this person already chose one out of those 365. So the probability that these two people have the same birthday is 1 minus this. Okay? Now, if we get to 3 people, well, it's going to be the same thing. First person can have any birthday they want, but the second person can have any day besides that one. The third person can have any day except the same as these two, so it's 2 less. If I had 4 people, we'd just continue on. If I had 5 people, I'd have this. So let's do some random calculations and see what that looks like. Okay, so here we go. 1 minus parentheses 365 divided by 365 times 364 divided by 365. So not a very good chance. Let's do the third one. 1 minus, and if you want to, you could do double parentheses. 365 divided by 365. Whoops. Times 364 divided by 365 times 363 divided by 365. So better chance than this one. Let's try 4 of them. So we're going to have the same thing, except for we're going to add a 4th one in here. So times 362 divided by 365. So now we're at least getting like 1 full percent, double of this one. Well, let's try 4 people. Or maybe that was 4. 2, 3, 4. Yeah, this is 5. So 361 divided by 365. So this is 5 people. There's almost a 3% chance. Let's jump up to 10. So I'm just going to do 10 people into here. So I'm going to need to do 5 more. So 360 divided by 365. That's 1. 359 divided by 365. That's 2. 358 divided by 365. That's 3 more. 357 divided by 365. That's 4 more. And it should be all right that I don't put a times there, but just in case. 356 divided by 365. I think that was 5 more. So now we're up to almost a 12% chance with 10 people. Okay, so we could carry on the pattern, but what you see is that with just 12 people, we're up to that percent. So I'll just type in a few more. I'll do 10 more. I'm not going to bore you by making you watch it, but I'll hit pause and type it in and then hit enter and you can see what it is. So the 10th new one is 346 divided by 365. Whoops. So with 20 people, we see the probability is almost 41%. So the probability that 2 people have the same birthday out of 20 people is 41%. So it doesn't take much more. And you can see that we'll be above 50%. So you'd have a better than 50% chance of choosing two people with the same birthday. If you want to see the numbers in your book, you'll have to look on page 583, and that'll show you some more numbers. So anyways, that'll give you some more probabilities with that. The money, this 3-door one, if you want to see some more examples of that, that's on page 9, page 16, and page 23 of your book. So if you want to see some more, try to get a better understanding at page 9, page 16, page 23. If you look for it on YouTube, you'll hear, or even on Google, look out for it on Google, you'll see some highly educated people try to explain it too. But anyways, it's the short moral of the story is you have better odds if you switch. And then 2 dice, all of the probabilities that make that up, and then 2 people that will have the same birthday. Here's a quick thought for you. Once you get above 25 people in a room, your percentage is up to 57%. So if you have more than 25 people in a room, odds are better than half that two people will have the same birthday. So when you get in a classroom full of 30 people, your percentage is very high. You're almost to 71%. So you start having those kinds of odds, you can start betting people, hey, I bet 2 people in this room have the same birthday with 30 people, and people are going to be like, no way. But if you get up to 40 people in a room, you're at 89% of the people. 89% of the time, you'll have 2 people that have the same birthday. So when you get to college, you can be like, hey, I bet that there's 2 people in this room, if you have a class over 40, that have the same birthday. You know, it'd be pretty rare. 1 out of 10 times, you're going to have 40 people that don't have the same birthday. So you'd most likely win that bet if you're interested in that one. So that's that story. So now on that worksheet I gave you that says Chapter 8 sample test questions, and it says Chapter 8.2. So if you look at the first one, theoretically it's possible to build a weighted die so that the probability of rolling a 1 is 1/3. So the probability of 1 is a 1/3, probability of a 2 is 1/6, probability of a 3 is also 1/6, probability of 4 is 1/12, probability of 5 is 1/12, and probability of 6 is also 1/12. Is this true or false? Remember, the probability of this all has to add up to be 1. So if you get common denominators, so if I multiply this one by top and bottom 4, I have 4/12. Top and bottom multiply by 2, that's 2/12. Top and bottom by 2, that's 2/12, and these are already in twelfths. So if this is to be correct, these should add up to be 12 over 12. So 4 plus 2 is 6, plus 2 more is 8, 9, 10, 11. So 11 over 12, no, that's not that's not theoretically right, okay? So somewhere there should be one of these that has a better chance than what it actually has. So the next one, it is more likely than not in an arbitrary group of 30 people, 2 people will share the same birthday, true or false. So that's this one that we just looked at with the same thing. 25 people is 57%, 30 people is 71%. So true, there is it is more likely, so more than 50% chance that they do have the same birthday. All right, the next one, suppose you're playing a game with 3 cards. So you have 3 cards. One of them is red on both sides. Okay, so we have a card that's red on both sides. We have a card that is blue on both sides. And we have a card, one side blue and one side red. Can't decide what it is. Okay. It says you're shown one side of the card and it's red. Well, if you're shown one side of the card and it's red, it's either this or this. Okay, it cannot be this card. What is the probability that the other side is blue? So given that one side is red, so this is red, red, and this is red, blue. So you're shown one side of one card and it's red. So we know that we are only looking at these two cards. Okay, this one is out of the picture. What is the probability that the other side is blue? Well, out of these two cards, what's the probability that I get red, blue? 50%, because there's only two cards that we're looking at. So what is the probability the other side is blue? 50%. Because it's either going to be red, blue or red, red. There's only two cards. One of them's blue, the other one's red, red. Okay? So it would have been different if we would have just said, what's the probability that one side is blue out of all of the cards? Or something like that. So that given makes things a little bit different. Now the next one, assume that the probability of having a boy or girl is the same. What's the probability of having all boys in a family with one child? Well, with one child, it's either a boy or a girl, so it's 50% chance. With two children, well, you can either have a boy, 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 girl, girl, boy, or girl, girl. So the probability of having all boys in this one is 1/4. A family with three children. So you could have a boy, 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 or a boy, boy, girl, or you could have a boy, girl, boy, or a boy, girl, girl, or you could have a girl first, and then a boy, and then a girl, or a girl, girl, boy, or you could have a girl and then two boys, or you could have all girls. So the probability of getting all boys is 1 out of 8. Okay, there's only one way out of 8. Part B, how many children must a couple have in order to have more than a 95% probability at least one of them will be a girl? So it says 1/8 is 0.125, 1/16 is 0.0625, and 1/32 is 0.3215. So when it says at least one of them will be a girl, it means the only thing we're going to do is take off all boys. So out of 4 of them, there's only 1 out of 16. So what's happening is each time there's 2 choices, so it's 2 times 2 times 2. So with one child, there's 2. 2 children, there's 2 times 2, which is 4. 3 children, it's 2 times 2 times 2. 4 children, it's 2, so there's 16 different choices we could have. 5 children, there are 32 different possibilities, but only one way out of those 32 is all boys. So at least one girl means 1 minus all boys. At least one girl means we're just going to get rid of the one that's just all boys, and these all have at least one girl. So 1 minus 1/16 is 15/16. And so you'd have to calculate what that is. 1 minus 15 divided by 16. Oh, whoops. 1 minus 1 divided by 16. There we go. So that's 94%. That's not quite there. 1 minus 1 divided by 32. There we go. That's above. So they would need to have 5 children on that. So the next question is the money. Let's make a deal. We've talked about that. The next question on your theme paper says, what's the probability of rolling a 6 3 times in a row with a pair of dice? So think of this as a sample space. I have 3 rolls. What's the probability of a 6 on the first roll? 1 out of 6. What's the probability of a 6 on the next roll? Well, I have 1 out of 6 chance. What's the probability of a 6 on my next roll? 1 out of 6. And then you multiply these probabilities together. Okay, so that's the probability of getting a 6 3 times in a row. Okay. Part B, selecting an ace from a regular deck of cards, given that a king was previously removed from the deck. A standard deck of cards has 52 cards, okay, 4 of which are aces. If I remove a king, I now have 51 cards, of which 4 are still aces. So part B is 4 out of 51. Part C, selecting an ace from a regular deck of cards, given that an ace was previously removed from the deck. So not only have I taken out one of these cards, so there's 51, but I've also taken out one of my aces, so there's only 3 aces left to choose from on part C, so it's 3 out of 51. Part D, randomly selecting a real number for which the digit 3 never occurs in its decimal expansion. Real number for which the digit 3 I'm not exactly sure what that one's asking. In the decimal spots, this would have, there'd be 9 out of 10 choices, and 9 out of 10 choices, and 9 out of 10 choices, and 9 out of 10 choices that wouldn't have a 3, but any number that's divisible. So if I take 4 and divide it by 3, that'll end up with 3's down here. 8 divided by 3 ends up with 6's. 7 divided by 3. So if I keep counting like this, every one of these divided by 3 will have repeating 3's, but there's just so many different options. I'm not sure that's maybe there's something that I'm not quite catching on that one. So anyways, we'll skip it. E, flipping a $50 coin 8 times and seeing at least one head. So this is much like the all boys or all girls problem. So if I have a head or a tail, I could have, oh, this is going to take forever. A head and a tail, right? Then I could have a head or a tail, or a head or a tail on my next one. And this could be a head or a tail, a head or a tail. This is only flipping it 3 times to get my, so what this is like saying I have head, 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 tail, head, head, whoops, that's supposed to be a tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. And then I go to the 4th one, and each of these I could add on another possibility with it. And so this would now be head, 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 head or tail, head, 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 tail, head or tail, head, tail, head, head or tail, head, tail, tail, head or tail, tail, head, head, head or tail, tail, head, tail, head or tail, 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 head, head or tail, 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 head, or tail, 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 tail. So anyways, that's just 4 of them. So 16 of them, 8 of them, 8 times, really that means we have 2 to the 8. Okay, so if I go 2 to the 8, there are 256 possibilities. But it says, seeing at least one head. Well, what that means is the only one that we aren't going to have is 8 tails in a row. So that's just 256. So remember, it's 1 minus. Hold on. 1 minus 1 over 256, which is 255 over 256. So this is the only way. There's one way out of 256s that's all tails. So flipping a $50 coin 8 times and seeing at least one head, 255 out of 256 times we're going to see at least one head. Okay, so anyways, that's how that problem works. Suppose I have rolled 2 dice and I announce that the sum of the 2 dice is 4 or less. Compute the probability that I rolled a total of 3. So if it's 4 or less, so 4 or less, that is this line. So 4 or less, there's 1, 2, 3, 4, 5, 6. So there are 6 of them, and 2 of them are 3s. So if it's 4 or less, the probability that I rolled a 3 is 1 out of 3. Okay, so 1 out of 3 on that. Part G, flipping a head or rolling a 2 after tossing a penny, a nickel, and a die. Flipping a head or rolling a 2 after tossing a penny, a nickel, and a die. So the penny could be a head or a tail. And then when I flip the nickel, it could be a head or a tail. Okay, so those are the 4 possibilities. This would be the penny, this would be the nickel. And then flipping a head or rolling a 2 after tossing a penny and a dice. Rolling a 2 is 1 out of 6 chance. So flipping a head, so getting a head, so any one of these that has a head would work. So there's 3 out of 4 of them times 1 out of 6. So that is 3 out of 24 or 1 out of 8. Rolling 2 fair dice and having the sum exceed 4. So you can look at the chart on that. So anyways, that's 8.2. This is a pretty good chunk of what will be on Chapter 8 test. So that's why I spend a lot of time on it. So anyways, sorry that it's a long video, and hope you're doing well and you get your feet wet with probability a little bit. So if you have questions, let me know, and I'll work through some more with you or try to explain or something. We can set up a video and we can talk about some ideas. So good luck and hope you're doing well.